You know, when we hear the term artificial intelligence, we usually picture these incredibly complex algorithms, maybe even sci-fi robots. But what if I told you that pretty much everything in AI, from the smart assistant in your phone to a self-driving car, is actually built on one single, really simple idea? Well, today, we're going to pull back the curtain on that fundamental building block, the AI agent.
So, let me ask you this. What do you have in common with a self-driving car? I know, it sounds like the setup to a pretty weird joke, right? But this question actually gets right to the heart of what AI is all about. You both share a fundamental design, and figuring out what that is, well, that's the key to understanding how AI sees and interacts with the world.
And the answer is, you're both what we call agents. Now, this is a simple idea, but it is incredibly powerful. The official definition is that an agent is anything that can perceive its environment through sensors and then act on that environment through actuators. To put it really simply, it senses the world and then it does something in the world. That's it. This two-part concept is the foundation for absolutely everything we're about to get into.
Okay, so let's break that definition down a little bit. What do we really mean when we say sensors and actuators? I know they might sound like technical, jargony words, but trust me, the concepts behind them are things you are using every single second of every day.
This comparison makes it all click, doesn't it? For you, a human agent, your sensors are your eyes, your ears, your sense of touch. You're constantly taking in data. A robotic agent, on the other hand, it's got things like cameras, microphones, or infrared sensors. And then to act, you use your hands, your legs, your voice as actuators. The robot uses motors, wheels, and speakers. See? It's just different hardware, but the core principle is exactly the same. Sense, then act.
All right, let's add two more crucial terms to our toolkit. First, a percept. A percept is just a piece of information an agent gets from its sensors at one specific moment. It's like a single snapshot of the world. Then you have the percept sequence, which is the complete history of every single snapshot the agent has ever taken. And this is so important. An agent's decisions are completely based on this history. It can only act based on what it has personally perceived.
Okay, so we get it. An agent senses and it acts. But how does it decide what to do? This brings us to a really important distinction, and that's the difference between the perfect, theoretical idea of an agent's logic and the actual real-world code that makes it happen.
So on one hand, you have what's called the agent function. This is the abstract, perfect blueprint. Think of it like a giant, flawless rulebook that tells the agent the single best action for every possible history of perceptions it could ever have. But on the other hand, you've got the agent program. This is the concrete code, the thing that actually runs on the machine. The program's job is just to try and implement the logic of that perfect function as best as it possibly can.
Now, you might see this in an AI textbook, and your eyes might just glaze over, but don't worry. This is just the fancy mathematical way of saying what we just talked about. That P star just means the percept sequence, the whole history. The little arrow means maps to, and the A just means an action. So all this equation is saying is the function f is just a rule that maps a history of perceptions to one specific action. See? That's all it is.
All right, enough with all the theory. Let's see how these pieces actually fit together in a real simple example. We're going to look at the classic case study that's used to teach AI, the vacuum cleaner world. Yeah, it's basic, but it makes everything we've talked about crystal clear.
So, here are the rules of the game. Our little agent, this robotic vacuum, lives in a world with only two rooms, room A and room B. Each room can either be clean or dirty. At any given moment, the vacuum's percept is just its current location and the status of that spot. So, for example, it might perceive room A dirty, and it has only three possible actions it can take: move left, move right, or suck up the dirt. Super simple.
And this right here, this is its brain. This is the agent function in its simplest form, just a little lookup table. This table is its entire logic. If the percept is location, dirty, the action is suck, no question. If the percept is location, clean, the action is to move to the other room. It is a perfect, direct mapping from every perception to a specific action. Simple, totally predictable, and for this world, it's really effective.
So we've designed a simple vacuum agent. It senses, it acts, it follows its little program. But so what? What's the point? This brings us to the final and honestly the most important concept, the ultimate goal of building an AI agent in the first place.
See, the goal isn't just to build an agent that does things. The goal is to build a rational agent. A rational agent is one that always acts to get the best possible outcome. And we define that best outcome with something called a performance measure. You can just think of it like a score. For our vacuum, the score might be 1 point for every clean square per hour. A rational vacuum, then, is one that always chooses the action it believes will maximize that score. It doesn't just clean, it cleans optimally.
And that leaves us with the big question, the one that drives so much of modern AI research. It's one thing to define rationality for a simple vacuum in a two-room world, but how do you define and measure it for a self-driving car in the middle of chaotic city traffic? Defining that performance measure, that score for success, and then building agents that can actually maximize it in our complex world, well, that's one of the biggest challenges in AI today. So what does it truly mean for a machine to be rational? That's the question at the very heart of this entire field.